A single language model, operating in isolation, is prone to fracturing. When tasked with multi-step logic, a zero-shot prompt forces linear generation without the capacity to pause, reflect, or correct its own trajectory. Because the model cannot reliably verify its own facts or catch logical drift during a single generation pass, relying on it for high-stakes tasks results in architectural failure. To mitigate the inherent fragility of these zero-shot responses, developers are shifting focus towards system-level architectures that wrap the model in a strict execution framework. One approach is designed for open-ended reasoning, research, and complex synthesis. This illustrates the divergence. On the left, we have dynamic reasoning. On the right is a second path, designed for execution-heavy tasks where technical precision is the only priority. Production-grade reliability requires choosing between two strategies: scaling test-time compute by forcing the AI to debate itself, or enforcing a rigid state machine through a strict constitution. Treating a language model as a simple text generator yields unpredictable results. Reliability in production requires an environment that either weaponizes internal friction or entirely eliminates model autonomy. This first method is visible in Andrej Karpathy's open-source multi-agent council architecture. The mechanism is straightforward. Instead of a single query, the system routes the user prompt to multiple specialized instances of the model simultaneously. Each instance runs on different system instructions. One acts as a researcher pulling live data, while another focuses on mathematical logic. They are forced to evaluate the problem from conflicting angles. This creates adversarial consensus. The agents exchange messages, cross-checking facts, and exposing weak logic in each other's work before producing a final answer. The contrarian agent is the most critical role. Its sole directive is to disagree. It searches for off-by-one errors, flawed assumptions, and alternative framings to attack the outputs of the other agents. In production environments, this internal peer review loop cuts hallucination rates by 65%. The system remains cost-efficient because all agents share the same prefix cache. The compute cost is only marginally higher, typically 1.5 to 2.5 times a single pass, rather than a full 4 times multiplier. By replacing a single point of failure with an automated review system, errors no longer correlate. The AI catches its own blind spots before the output ever reaches the user. Debate is effective for research, but it introduces risk when an AI is granted direct write access to deployment tools, to production databases, or cloud infrastructure. For execution-heavy environments, engineers rely on constitutional determinism, utilizing frameworks like the Nexus Constitution. This system strips the model of its conversational nature. It forces the model to operate as a strict state machine, processing data through a rigid, sequential pipeline. If a security or cost constraint violation is detected, the hard stop protocol activates. The system cannot proceed, and it cannot warn the user. It must instantly abort the operation and force a correction. The Constitution mandates rigid structures. Any architectural blueprint generated must conform to a non-negotiable 7-part output plan, including the mandatory cost and security validations. Personas within the system are highly restricted. An agent acting as a grid architect is forbidden from generating prose. Its outputs are confined to strictly formatted CSV grids. Every work order concludes with a validation script that returns a mathematical pass or fail. This removes subjective interpretation from the AI's execution path. In high-risk environments, the architecture functions as an inescapable set of rules, ensuring the only possible output is a safe, highly constrained action. Executing these systems at scale requires specific API-level optimizations. Without them, latency and compute costs become prohibitive. Prefix caching is the critical optimization here. By wrapping system instructions in XML tags, the API stores that context in memory. To maintain the cache hit, the prompt history must remain static during iterative tool calls. Altering the prefix forces the model to reprocess the entire context window, destroying the cache. Modern systems use native tool calling rather than relying on the model to generate XML-based commands. An agentic architecture will fail in production if the API calls are not structured to minimize token reprocessing at every step of the loop. Prompt engineering has transitioned into systems engineering. Architects must now select their deployment model based on the risk and complexity of the task. This matrix provides the framework for modern AI deployment. Utilize the debate architecture when you need to synthesize research, verify logic, or maximize accuracy in open-ended problems. Conversely, utilize the dictate architecture whenever the AI is granted access to databases, cloud infrastructure, or financial tools. Applying debate to a database, or strict dictates to creativity, results in total system failure. The era of trusting a single model to get the right answer immediately is over. Reliability now belongs to engineers, who either force the machine to argue with itself or lock it into a system of inescapable rules.